Welcome to the next video in the systems programming video series. We are continuing in the textbook Dive into Systems, and we are skipping section 7.4 because, we're following a retired course, and the reading assignment for the course has us skipping to 7.5. So recall, as I've mentioned earlier, that RSP, that's the stack pointer, it always points to the very top of the stack, and coincidentally that means that it is always pointing to the top of the current active frame. And we have RBP, that is always pointing to the base, the bottom of the current active frame. So if we check this diagram here, then if we imagine that main has its stack diagram down here somehow, and at some point, it has its RSP was at some point at this location in address, but then as soon as this fname function is called, then what standardly happens is that we push the base address, right, the former base address, which was this 42C in hex, we push that onto the top of the stack. That now, right, this now becomes the RBP, the base pointer, because it's at the base of the new active frame. And so that's why in this diagram, 418 is the address of the base pointer, but what it holds in that address is the old address of the base pointer for the frame that is immediately below in the stack. So in this situation, we would say that the main function is the caller function, the fname is the callee function. I guess the one thing that we haven't really talked about in earlier videos that we should is that we tend to also, when calling on a function, put at the top of the stack, right, but before calling on the, some other function, we put onto the top of the stack the return address, which is the address that indicates where the main function program execution resumes once calling fname has finished. And so this is worth emphasizing is RBP and RSP are pointers to the stack, right? Or memory, stack memory. RIP points to an address in code segment memory, right? So, I think we saw this the last time we did a walkthrough with assembly code where like the addresses for RIP were entirely independent of the addresses that were being managed and handed around for the stack information. So this return address is a return address for code segment memory. Now there are also these functions, leave queue, call queue, return queue. So what does leave queue do? It moves the base pointer, right, the current base pointer into the stack pointer, which is typically because if you think, maybe I can point back to this diagram over here, that the base pointer is here, right? RBP is here. And when you're trying to exit the call to the, to the callee, right? When you're leaving this thing, then you want RBP to go back down to here, but also you want RSP to come down to where RBP is. So that explains why we are calling move into RSP. That is causing this transition, right? Reassigning the value of RSP to be the current location of RBP. So that's what this move is doing. And then pop removes the top of the stack and puts it into RBP. So what is that? Because that is RSP. RSP has now been moved to the same location as the location of RBP. So when we pop, that is going to take the value at RSP, right? You can go back and refresh yourself on what pop does, but it will take this value here where RSP is, and load it into RBP, because that's what we're saying to do. We are loading this pop value into the destination, pointed to the wrong place. This RBP, right, that's where we're storing this. So this address, which remember is the old address of this base pointer down here, we're now moving that into RBP so that now RBP is coming down here. So effectively this pop command is causing RBP to get shifted down to the old base pointer location. And not only that, but RSP, because again, remember how a pop operation works, it also moves the stack pointer, it adds 8, so moves it down to this address, which is back to being a pointer to the top of the stack. So anyway, long story short, leave Q kind of exits the callee frame and puts all the pointers, or puts all the stack pointers back to where they need to go to hand control back over to the caller frame. Then call Q, if you give an address, will perform these two functions, which basically takes the instruction address and pushes it to the top of the stack, and then reassigns the value of the instruction pointer, right? So basically, this address should be the address of the instructions for the callee function, right? So basically what this is saying is that instruction register should get switched over to the addresses that hold the instructions for fname, right? I hope that's clear. I'm not sure if I know how to explain that any clearer. And so this is what you do afterwards, right? So if call Q had pushed the instruction pointer to the top of the stack so that it could be used later to remember where the instruction counter is supposed to return after the function has finished, well, return is the command that is going to pop exactly that value off the top of the stack so that it can go back and remember where it was supposed to continue executing. So I hope that's fairly sensible. Here we have function parameters. We've already kind of talked about this. I don't think we're going to need to know, at least for a little while, we're not going to need to know much more than RDI being the register for parameter 1 of any function. And so now we're going to trace through an example. And this I think it's going to get quite long, and I'm worried that if I try to fit it all into a single video, it'll be a very long video. So I might just plan to introduce this example, maybe talk about just the very first part of the setup, and save the entire walkthrough for the next video. But anyway, so what we're going to have is we're going to have two functions. And notice, by the way, that we're putting the word void inside the function. And basically, when you do that, it's not necessary. It's like the exact same behavior as if you simply gave no arguments at all. But by putting void there, it causes the assembly that comes out of the compiler to just look a little bit more sensible. So it's not necessary, but it's going to help the assembly code later on. So don't worry about it if you're wondering what that is. It's not important. Just treat it as if these functions have no arguments at all. Now, assign is going to create a variable, which is, it'll be worth sort of clocking how things are different when you merely declare a variable versus how things look when you both declare and initialize a variable. But anyway, so assign is going to initialize a variable and then return that variable, whereas adder is going to declare a variable but then never initialize it and immediately return it, which of course I think we all probably have the instinct that that's going to cause weird behavior, and to some degree that's the point of this example. But anyway, so we have these two functions, and they're going to get called in the main function. So what does the main function do? Pretty straightforward. We declare x, we call the assign function, we assign to x the return of adder, and then we print x and return. So I think that's fairly straightforward. We can see when we do an obj dump to the executable that is generated by this program, then we can look directly at the assembly for assign. We can look at the assembly for adder, and we can look at the assembly for main. So here we're going to get started by looking at a walkthrough for main. And so we can see all the assembly with all of the relevant addresses for the instructions. And of course, as always, at the call of a function, we push the base pointer and we move the stack pointer into the base pointer register, I guess maybe I should say. But in any case, these two things are kind of boilerplate for a function call, and we've already talked about the logic of this in a previous video, so I'm not going to belabor the point here. In the next video, I'll talk about the remaining lines of code. But before any of that, even before any of the code runs, right, if we think that none of this code has run at all, then we mostly imagine that the registers are full of garbage values. I don't know, does anything here have a meaningful value? Well, I guess the stack pointer, like even before the function executes, the stack is somewhere. And so the stack pointer, just even before the function starts to execute, has a meaningful value. And the instruction pointer has a meaningful value because when you're executing a function, you got to know where to start. So the stack pointer has a meaningful value. It really is pointing to this location in memory that is done deliberately by whatever is executing your program or compiling your program. And your instruction pointer is meaningful, but all of the rest is really just garbage values. They don't mean anything. Okay, and here we'll start looking at the instructions of the first line of assembly, but let's, because this is a long walkthrough, so let's save that for the next video.